In 2007, the Smithsonian Institution was approached by the Swedish Embassy in DC and asked if they would like to borrow a very special item. This particular object would be displayed at the museum under guard for 2 days and would be the spark for a symposium at which international scientists would give lectures. What was this object? What was it that could inspire such excitement? A fabulous diamond or ruby? An incredible dinosaur or mammoth fossil, perhaps? No, the object was a book, a first edition of a book that was actually the personal copy of the author. It was a book that was published in 1735, some 125 years before Darwin's On the Origin of Species, but a book, like Darwin's, that had a profound effect on biology and paleontology. That book was the Systema Naturae, and its author was a very colourful character called Carl Linnaeus. In this episode, we are going to be considering one of the fundamental underpinning pillars of paleontology, the science of classifying and naming organisms, the science of taxonomy. Now, to some, this might sound somewhat, trivial, but trust me, without it, there would be no paleontology. So in this episode, we will ask, who was Carl Linnaeus? And what is Linnaean classification? How is taxonomy different from paleontology? And why is classification important in paleontology? So who was this extraordinary man who could inspire an ad hoc international conference at the spur of a moment? Linnaeus was born in an exciting time, the time of the Enlightenment, also known as the Age of Reason. From the late 1600s to the early 1800s, there was a great flowering of debate and questioning of traditional views and authorities, a time when there was much talk of societal reform and tolerance, a time when scepticism and science were the touchstone for debate. It would see the emergence of philosophers like Descartes, Voltaire and Hume, and scientists like James Hutton, the founder of modern geology, Antoine Lavoisier, one of the founders of modern chemistry, and physicist Sir Isaac Newton. And there was Carl Linnaeus, born 23rd of May 1707 in the countryside of southern Sweden in Rashult. His father was a Lutheran minister, but probably more importantly for science, Niels Ingersollman Linnaeus was also a keen amateur naturalist and avid gardener. It is probably from this that Linnaeus got his lifelong love of plants. In 1727, he went to Lund University to study medicine, but transferred to Uppsala a year later to continue his studies. Apparently, the standard of medical training was not of the highest quality, so he spent most of his time just collecting plants. He got such a reputation for botany that he was asked to teach at the university as a lecturer. By 1732, and only in his mid-20s, he was leading an expedition to Lapland, where he'd become fascinated with the local Sami people, and in particular their use of medicinal plants. He published details in Flora Laponica in 1737, probably making him one of the world's first ethnobotanists. You can see Linnaeus pictured here, dressed in native clothing of the Sami. He is also holding a sprig of the twin flower, an emblem that features in many of the paintings of Linnaeus. The plant was named scientifically for him, Linnea borealis, and described as shy and timid as the person after which it was named. Which is somewhat amusing, as Linnaeus, although never grand in stature, he was only about 5 foot tall, was certainly a grand master of self-promotion. He called himself the general of Flora's army and referred to his graduate students as his apostles. Not too surprising then that he wrote at least 5 autobiographies. Linnaeus returned to his medical studies in 1735, but in the Netherlands rather than Sweden, where he would graduate as a medical doctor at your Get Your Degree Quick University of Hadjewijk. He would present a written thesis on the cause of ague, that's malaria, which was a common disease in Sweden during the 18th century and often called Uppsala fever. He identified that the ague was linked to areas with damp clay soils, but assumed that the disease was caused by clay particles getting stuck in people's blood vessels. Although we know that this is wrong, Linnaeus was far too early for the high-powered microscopes that could identify the parasites in mosquitoes that actually cause this disease, you still have to admire his observational skills with linking ague to poorly drained land. Following this, he was questioned by examiners and required to examine and diagnose a patient. After this process, he received his degree, and in the space of just 2 weeks, he was graduated as a doctor at the age of 28. He would specialise in the treatment of syphilis. Financially, a very prudent thing to do, as one of the main treatments for syphilis was mercury. Mercury would treat some of the symptoms, but not the disease itself. As a result, your patients were always repeat patients. Hence the phrase, "One night in the arms of Venus leads to a lifetime on Mercury." For paleontologists and biologists, though, 1735 would see something even more significant, because this was the year of publication of the first edition of that most important book we mentioned earlier, the book that was guarded at the Smithsonian Institution's National Museum of Natural History for 2 days, over 270 years later, and about 4,000 miles away from where it was first published. The system Naturae represents Linnaeus' desire to bring order to creation. He saw it as his mission to bring back to nature the order that had existed at the beginning. He became known, probably much to his great delight, as the second Adam, naming creation just as the first man had in the Garden of Eden. As he said about himself, his favourite topic next to plants, Deus creavit, Linnaeus deposuit. That means God created, Linnaeus organised. Just as Newton has uncovered God's mathematics, Linnaeus wanted to uncover God's classification. In the Systema, all of creation is organised into 3 major kingdoms. Each of those kingdoms is divided into subgroupings of class, order, genus and species, significantly fewer than the subdivisions we have today. Naturalists before Linnaeus often used a somewhat arbitrary grouping of creatures, though. For example, groupings that comprise all creatures that live in water, or all domestic animals. Linnaeus was one of the first to group genera into higher taxa based on somewhat logical similarities. So what were Linnaeus' 3 kingdoms? Firstly, the animal kingdom, comprising the mammalia, that's the mammals, then the aves, or the birds, amphibia, that included at that point also the reptiles and the non-bony fish, insecta, that's all arthropods, not just the insects, and the vermes, basically all other invertebrates including worms, mollusks and echinoderms like sea urchins. In the first edition of Systema Naturae, Linnaeus still included whales with fish, but by the 12th edition they were placed in the mammals. He also correctly placed bats in the mammals and, horror of horrors, included humans along with the apes in the primates. Secondly, the plant kingdom. Here Linnaeus creates a system of 24 classes of plants based on the number and organisation of a plant's sexual organs, the male stamens and the female pistils, and related reproductive features. This wasn't without controversy, though. The way Linnaeus would focus on the sexuality of his classification offended some, and to be honest, Linnaeus did sometimes kind of get carried away in his descriptions. For example, the flower's leaves serve as bridal beds which the Creator has so gloriously arranged, adorned with such noble bed curtains and perfumed with so many soft scents that the bridegroom with his bride might there celebrate their nuptials with so much the greater solemnity. You got to admit, it's a bit over the top. Contemporary botanist Johann Seidsbeck called it loathsome harlotry, which may also explain why Linnaeus named the stinky weed St. Paul's wort Sigebeckia orientalis in his honour. Thirdly, the mineral kingdom. Now this might sound strange to us today, but in Linnaeus' time, many believed minerals possessed a basic kind of life force, and as such form a part of Linnaeus' system of classification. It was divided into the petrae, which is all the rocks, the minerae, that's minerals and ores, and the fossilia, fossils and aggregates. Linnaeus published 12 editions in his lifetime, continually revising and updating his classifications. The manner in which we order life today is quite different than much of Linnaeus's original efforts, but much of the legacy of his efforts is still with us. We still have a hierarchical organisation of life, and of course, we still have the scientific binomial system. In the days before the system of nature, naming creatures could be quite messy. Take, for example, the tomato. Prior to Linnaeus, it went by the rather grand and long-winded name of Solanum cocae inamiri herbaceae folis pinnatis incisis, which basically means the solanum with the smooth stem, which is herbaceous and has incised pinnate leaves. Under the Linnaean binomial system, it becomes Lycopersicon esculentum, much less of a mouthful. Because of the hierarchical system of the system Naturae, you don't need to list all the descriptive components of a species. All you need is the name of the genus followed by the name of the species. For example, Passer domesticus, the house sparrow, or Acheta domesticus, the house cricket. It's a simple but powerful system. As you can see, the species or specific name of any member of a genus could be used for other different genera, like domesticus in our example, which is also used as the species name of several other plants and mammals. However, genera will always be unique. Today, the system of classification used by many biologists and paleontologists is a system called cladistics. Cladistics considers the shared and derived characteristics of creatures when classifying them, rather than a superficial appearance. For example, under cladistics, there is no grouping called fish or class Pisces, as the group is traditionally understood. As we covered in A New History of Life, when you actually study the characteristics of certain fish, for example, a lungfish and a cod, you'll find that a lungfish shares more features in common with a frog than it does with a cod, even though a lungfish under the Linnaean system would still be classified under Pisces, the fish. In cladistics, by contrast, only groupings that contain all their descendants can be considered as a legal classification, or what is defined as, among those in the know, monophyletic. In classification, using cladistics, relationships between organisms are illustrated using a cladogram, a branching diagram of relationships supported by derived character states. For example, on this cladogram, the tiger, gorilla, and human can all be classified as mammals that share common features such as hair, somewhat vicariously in my case. If you just define a group called reptiles, that includes our friend the lizard here, as a group, it does not include all of its descendants, tigers, gorillas, and us in this case. And so reptiles is an illegal grouping and therefore are deemed paraphyletic under cladistic terminology, and you'll have the cladistic police knocking on your door. Reptiles are, however, part of a larger legal monophyletic group that contains animals called the amniotes, a group that contains all animals that lay eggs adapted to be laid on land or retain the fertilised egg within the mother. Let's now consider how the classification schemes might be different when used by a paleontologist. Remember that Linnaeus placed fossils within his mineral kingdom under fossilia? Unlike rocks and minerals, the binomial system for paleontology persisted, understandable given that we're dealing with former life. And the zoological or botanical codes of taxonomy that apply to living animals and plants likewise apply to the fossil forms too. The obvious problem we have with fossils compared with living creatures is, well, it's just that. As fossils, a lot of the information that could be used to classify these creatures is simply just gone. As such, drawing lines between species can be difficult. Just imagine how different human beings can look depending on their sex, their age, their historical background, and what environment they might be living in. Add to that the problem that paleontologists may be dealing with incomplete, fragmentary, or otherwise modified material, and the problem is just compounded. For a biologist, differences within the same species can be tested by simply observing that living species, watching how a species develops and changes over time, recording differences that might occur to the same species due to maybe environmental factors. And if you observe two individuals mating, however different they might look superficially, and still producing viable offspring, you can be sure that they are of the same or at least very closely related species. Today, biological classification is further aided by studying the genetic similarity between creatures, allowing us now, more than any time before really, to start to place life into real groupings based on real genetic similarity. Once again, this, with the exception of rare and fairly recent fossils, is not available to the paleontologist. To illustrate some of the problems that paleontologists face, I'd like to introduce you to some of the most iconic of the dinosaurs: Brontosaurus, Stegosaurus, and Triceratops. Three very familiar dinosaurs discovered by famous paleontologist Othniel Charles Marsh in the late 1800s. Of the three dinosaurs we are considering here, I must admit, I think Brontosaurus is my favourite. Back in the early 70s, when I was at elementary school, I remember drawing pictures of this long-necked behemoth wallowing in tropical Jurassic swamps to support its vast bulk, one of the pervasive and actually inaccurate views of the ecology of the creature at that time. The thing is, though, since 1903, there was no Brontosaurus. Brontosaurus was part of a treasure of dinosaurs recovered from the western USA by famous dinosaur hunters like Marsh and Cope during the 1870s. Marsh discovered the skeletons of two partial sauropod dinosaurs, that's the group to which these four-legged, long-necked dinosaurs belong, and sent them to the Peabody Museum at Yale. The first specimen he got round to describing he named Apatosaurus ajax, or deceptive lizard. We have a bone of an apatosaur right here. 2 years later, in 1903, he named the second skeleton and decided it was sufficiently different not only to be considered to be a different species, but also a completely new genus. As such, Brontosaurus excelsus, or noble thunder lizard, was born. After Marsh described these two specimens, skeletons belonging to similar sauropod dinosaurs were excavated, and upon analysis, it was determined that one species fell on a morphological spectrum somewhere between Apatosaurus and Brontosaurus. As such, the differences between the two end members of the group didn't appear so extreme after all, and the skeletons, including the new species, were all placed in the same genus. Taxonomically, the first named specimen has precedence, so all of these animals became apatosaurs, with Brontosaurus excelsus named to Apatosaurus excelsus. They had all become deceptive lizards. When you make a taxonomic determination, you're effectively proposing a hypothesis regarding the position of a particular living or fossil organism within the 4 billion-year-old tree of life. Any new information, such as data from new analytic techniques or additional specimens, may help revise that hypothesis. For our friend Brontosaurus, new information will be released in a paper by British and Portuguese paleontologists in 2015 by Benson, Matthias and Schoff. Now, determining when some fossil is sufficiently different from another to be placed in an entirely new genus is not strictly governed by any clear taxonomic guidelines. A kind of a judgment call has to be made. Since the time that the genus Brontosaurus had been demoted, however, new sauropod specimens had been recovered, and these paleontologists took advantage of the new discoveries to apply an extensive, the paper was 300 pages long, statistical analysis of the differences between various features of these animals. In concentrating their analyses on the broad group to which the apatosaurs belong, that's the diplodocid dinosaurs, they found that the differences between widely accepted genera within the diplodocids were at very least the same as the differences between Apatosaurus and what Marsh had originally described as Brontosaurus. Much to every 6-year-old's delight, and mine, at least according to the authors of this paper, Brontosaurus could be officially resurrected as one of the coolest dinosaurs of the Upper Jurassic. This shows how taxonomy, far from being the dusty old unchanging science of classification, is dynamic and potentially subject to change with every new discovery that's made. Another example of how we have to be careful with taxonomy comes from another dinosaur favourite, Stegosaurus. An exceptional discovery of a Stegosaurus graveyard in Montana has permitted the analysis of a large, well-preserved population of stegosaurs. We all know what Stegosaurus looked like, right? There's one right back there. The dinosaur with the tiny head and the spiky tail and rows of plates along its back. Like Brontosaurus, this dinosaur was originally discovered and named by Marsh in 1877 from the Jurassic Morrison Formation in southwestern Wyoming. Initially, Marsh thought that the Stegosaurus plates lay flat on its back like shingles. Hence the name Stegosaurus, or roofed lizard. Marsh would later rethink his interpretation, giving us the classic spiky-backed dinosaur we all know and love today. The discovery of a stegosaur graveyard in Montana presented a rare opportunity to study a larger population of well-preserved specimens, an opportunity taken up by graduate student Evan Saiter of the University of Bristol in the United Kingdom. When considering the overall morphology of the stegosaurs and the microscopic bone structure, Saiter was able to determine that all the stegosaurs found in this deposit were adults and that they all belonged to the same species, Stegosaurus majosi. Even so, there was a particular difference he found in the shape and arrangement of plates on their backs. Some specimens had plates that were pointed and tall, while others possessed plates that were broader and more rounded. So what are we looking at here? Saiter suggests that this could represent sexual dimorphism in the dinosaurs, or, in other words, differences between boy stegosaurs and girl stegosaurs. He proposed that the broad, round plates belonged to the males and the tall, pointed plates to the females. He bases his hypothesis on the size of the rounded plates that are some 45% larger in area and may therefore represent a display investment by the male, not unlike the large antler rack you find on deer or moose. Although this hypothesis is not accepted as evidence of sexual dimorphism by all, this does illustrate how we need to be careful when naming our dinosaurs or any other fossils. It's possible that if fewer, more poorly preserved specimens were recovered, these two forms could have been misinterpreted as two different species rather than the male and the female of the same species. And so to our third dinosaur. This one was discovered near Denver, Colorado in 1877 and originally described by Marsh as a bison, Bison alticornis. However, he eventually realized they belonged to a horned dinosaur he named Triceratops, another crowd-pleasing dinosaur. A controversy would erupt regarding this particular dinosaur in 2009 when paleontologist Jack Horner from the Museum of the Rockies and his graduate student John Scanella would propose a hypothesis at a conference at the University of Bristol that would significantly reduce the number of dinosaurs we have on the books. They suggested that Triceratops and Torosaurus, another horned dinosaur discovered by Marsh, were one and the same species, with Triceratops being the juvenile and Torosaurus the adult. They even proposed an intermediate teenager in the genus Nedoceratops. These dinosaurs look quite different though. Torosaurus has a much larger frill that is perforated with a large oval hole, perforations that are lacking in Triceratops. Although these animals overlap in time, they are regarded as being so different that they were not only different species, they were also different genera. However, Horner and Scanella take a different view. They claim that these differences just reflect different developmental stages of the same dinosaur. They believe Triceratops to be the juvenile, Nedoceratops the intermediate teenager, probably somewhat sullen and always wanting to borrow your car, and Torosaurus the adult, who really didn't understand Nedoceratops and thought his music was all noise. Horner and Scanella claim that microscopic study of bone textures among these animals show how the bone was transforming as the animal matured in what is called a metaplastic manner. For example, according to Horner, bone in Triceratops was reabsorbed from the centre of the head shield as the dinosaur matured and then redeposited around the margin of the structure, forming a distinctive rim in the shield of Torosaurus. This is still a very controversial hypothesis. Many paleontologists claim that the Tri-Nedo-Toro sequence doesn't always appear to be consistent. In addition, analysis is hampered by the relative scarcity of postcranial, that's anything other than the head, skeletons. Other criticisms have been levelled due to the presence of fused bones, indicating that growth had stopped in the proposed younger forms of the sequence. Nevertheless, Horner and Scannella point out that details of skull-bone fusion are very variable in the some 100+ specimens they hold at the Museum of the Rockies, and so the debate continues. If Horner and Scannella are proved to be correct, it would mean we lose Nedoceratops and Torosaurus as valid Linnaean genera, all of them becoming different growth stages of Triceratops, which, as described first, takes taxonomic precedence. Horner thinks that this could be part of a wider problem. He estimates that perhaps over 1/3 of all dinosaur species in the late Cretaceous, where Triceratops is found, may never have existed. He believes many just may represent different growth stages misinterpreted as separate species, as a particular dinosaur matures from a juvenile through the temporal teens, could you imagine a teenage dinosaur, and into an adult. Other examples of mistaken species could include Anatotitan, that some have suggested is just an adult Edmontosaurus, and the wonderfully named Dracorex hogswartzia. Yep, it was named for the Harry Potter books, and Stigmolox may just be growth stages in the development of the hard-headed Pachycephalosaurus. But why should we care about taxonomy and classification? It may appear that these questions are very academic, nothing more than the grumblings of academics about how to arrange their baseball cards by year, by team, by state. Does it really matter? But just consider the debate sparked by the classification of Triceratops, Nedoceratops and Torosaurus. If we accept the views of Horner and Scannella regarding the number of real dinosaur species at the end of the Cretaceous, we have a much more impoverished dinosaur population than we previously thought, prior to the impact of the extraterrestrial body that marks the Cretaceous-Paleogene extinction at 66 million years ago. This would give us a very different understanding of the paleoecology and stresses that this formerly successful and very biodiverse group may have been experiencing prior to their final extinction. The ongoing process of the classification of fossils helps deepen our understanding of biodiversity over time. Taxonomy refines our focus through the deep time window paleontology affords us. This is vital, as paleontology is our only long-term benchmark against which we can compare modern changes in the biodiversity and the current health of our ecosystem. Far from being a dusty old science of the past, paleontological taxonomy and classification could prove vital in charting our planet's future.